Hello students, my name is Kevin Zhang and I am a professor of quantum physics at MetaU. I graduated from MIT at the age of 14 and have been passionate about quantum mechanics and its many applications ever since. Today we will be discussing the concept of path integrals in quantum mechanics. This is a powerful mathematical tool that allows us to compute the probability amplitude for a quantum particle to travel between 2 points in space-time by summing over all possible paths that the particle could take. This concept is fundamental to many modern developments in theoretical physics and is used in a wide range of fields, including particle physics, condensed matter physics, and quantum information. So let's start by taking a closer look at the mathematical formulation of path integrals. The probability amplitude for a particle to travel between 2 points in space-time can be expressed as a path integral. P equals sine dx es t. Here, xt represents the position of the particle at time t, sxt is the action of the particle, and h is Planck's constant. The integration is taken over all possible paths that the particle could take between the 2 points, represented by the variables dxt. Now, one of the key advantages of the path integral formulation is its flexibility in dealing with non-equilibrium systems. This is because the path integral involves a time-ordered product of operators, which accounts for the evolution of the system over time. This is different from the Schrödinger equation, which is only valid for systems in equilibrium and is formulated in terms of a single Hamiltonian operator. Another advantage of the path integral formulation is its connection to the concept of symmetry in physics. The path integral can be formulated in terms of a Lagrangian, which encodes the dynamics of the system and its underlying symmetries. By manipulating the Lagrangian, we can study the effects of various symmetry transformations on the system's behavior. For example, in particle physics, the symmetry of the strong force is described by the SU-3 gauge symmetry, which is encoded in the Lagrangian of quantum chromodynamics. Now let's turn to some practical examples of path integrals in action. One such example is the Feynman path integral, which is used to compute the probability amplitude for a particle to move from an initial position to a final position. This technique was developed by Richard Feynman, a physicist who is perhaps best known for his work on quantum electrodynamics, and has been used extensively in both particle physics and condensed matter physics. Another example of the application of path integrals is in the study of topological phases of matter. These are exotic states of matter that cannot be described by local order parameters and are characterized by topological invariance. Path integrals are used to study the behavior of these topological invariants under various perturbations and have led to many interesting discoveries in the field of condensed matter physics. Finally, let's make a fun connection to a popular movie, Interstellar. In the movie, the character played by Matthew McConaughey travels through a wormhole in space-time to explore a distant planet. The concept of a wormhole is related to the mathematical concept of a geodesic, which represents the shortest path between 2 points in space-time. Path integrals can be used to study the behavior of particles traveling along geodesics, and have been used to model the behavior of black holes, wormholes, and other exotic space-time phenomena. In conclusion, path integrals are a powerful mathematical tool that allows us to study the behavior of quantum systems in non-equilibrium and non-perturbative regimes. One important concept related to path integrals is the idea of gauge symmetry. Gauge symmetry is a fundamental aspect of modern physics and is essential for understanding the behavior of particles in the presence of electromagnetic and other fields. The concept of gauge symmetry can be understood using the principle of least action, which states that the path taken by a particle between 2 points in space-time is the one that minimizes the action, or the integral of the Lagrangian over the path. Gauge symmetry arises when there are multiple paths that give the same value of the action. This is because the Lagrangian depends not only on the position of the particle, but also on the gauge potential, which describes the electromagnetic field. The gauge potential can be changed without affecting the physics of the system, since it only represents a mathematical artifact of the way we choose to describe the electromagnetic field. This means that there are many different ways to describe the same physical system, each corresponding to a different gauge potential. The different gauge potentials are related by gauge transformations, which are a kind of symmetry transformation. As we delve deeper into the concept of probability and wave functions, we begin to realize the vast potential they hold for predicting future outcomes, especially when combined with machine learning algorithms. The ability to predict future outcomes with a high degree of accuracy has been a long-standing goal of science and technology, and has significant implications for fields ranging from finance to medicine to weather forecasting. At the heart of this predictive power lies the concept of quantum computing, which promises to unlock new levels of computational efficiency and speed, even for problems that are currently unsolvable by classical computers. The key to this power lies in the ability of quantum computers to exploit the properties of quantum mechanics to perform computations on a massive scale. This includes the ability to perform complex calculations involving probabilities and wave functions, which are fundamental to many areas of science and engineering. One of the most exciting applications of quantum computing is the potential to create a kind of time machine by using quantum algorithms to predict the outcomes of future events. By analyzing the probabilities and wave functions of various outcomes, it may be possible to generate highly accurate predictions of future events, allowing us to effectively travel forward in time. This concept may seem like science fiction, but it is already being explored in some areas of research. For example, in finance, quantum computing algorithms are being developed to predict market trends and optimize investment strategies. In medicine, quantum computing could be used to predict the outcomes of various treatments, allowing doctors to choose the most effective course of action for each patient. And in weather forecasting, quantum computing algorithms could be used to generate highly accurate predictions of severe weather events, allowing people to prepare and take appropriate action. But to fully harness the power of quantum computing, we must first develop a deep understanding of the mathematics and physics that underlie it. This includes not only the concepts of probability and wave functions, but also the principles of quantum mechanics and quantum field theory. These fields are notoriously complex and difficult to understand, requiring a high degree of mathematical proficiency and deep conceptual understanding. Moreover, the development of quantum algorithms for predicting future outcomes will require a deep understanding of machine learning algorithms, as well as the principles of data science and artificial intelligence. This will require interdisciplinary collaboration between physicists, mathematicians, computer scientists, and engineers, as well as significant investment in research and development. In conclusion, the concepts of probability and wave functions are at the heart of quantum mechanics and quantum computing, and hold significant potential for predicting future outcomes in a wide range of fields. By combining these concepts with machine learning algorithms and other advanced technologies, it may be possible to create a kind of time machine, allowing us to predict the outcomes of future events with unprecedented accuracy. However, realizing this potential will require a deep understanding of the underlying physics and mathematics, as well as interdisciplinary collaboration and significant investment in research and development.